Muchísimas gracias a todos. De verdad que es un verdadero honor tener a la profesora Katherine Mirica. Veo que hay más gente, si quieren pasar, sentarse por acá. Y les agradecemos mucho que estén aquí. It's my absolute pleasure to have this wonderful opportunity where we are going to see magnificent chemistry, but most importantly, is the applications that Katherine is actually doing in her research. To attempt to do an introduction of Professor Mirica would be quite challenging. So many credentials and so many interesting achievements that she has already got that probably I would need like half an hour to properly introduce her. Taking the advantage that she's also a great collaborator and friend of us. Needless to say, one of the most remarkable chemists that I ever met. And a little bit of a story, how we met, is through her fantastic chemistry when I was reading about detection of H2S and other toxic molecules. So immediately, our research group became a fan of Katherine's work, and luckily we met last September in Sweden, and that's how we started. So I'm pretty happy to see so many young faces, because the main idea is that this talk is for you. Apart from getting inspired about the chemistry that Katherine is developing, some of you perhaps are going to be doing their PhD at Dartmouth College. Beautiful place. So with all of that, Katherine, the floor is yours. Thank you so much.
Thank you. Thank you so much for that kind introduction. It's my absolute pleasure to be here and have the opportunity to share some of the work that my group has been doing at Dartmouth for the past 8 years or so. So before I jump into the science, I just want to give you a little bit of a view of where I'm coming from. I'm located in Hanover, New Hampshire, which is about a 2-hour drive north of Boston. And Dartmouth College is one of the colonial colleges in the United States. It's one of the Ivy League institutions and was founded before the American Revolution. So it's technically older than the USA itself. The enrollment is relatively small. This is a private university, so we have a total of 6,000 students, and then graduate enrollment is around 2,000. That includes professional schools like medical school, engineering school, business school. And our graduate programs are mainly in the sciences. The humanities are mostly undergraduate, so we have this kind of split personality of being a college, but also a university. So that's where we are. This is the chemistry building, and if anyone ever wants to come visit, please do let me know and get in touch. So as we jump into the science, I just want to give you a broad overview of what my group does. We work across a range of length scales, ranging from molecular solids to network solids to macroscopic functional devices. And in all these realms of materials, we look to capitalize on the emergent properties of materials that are greater than the sum of the molecular components that we put into the system. So with that goal in mind, we have 3 major thrusts. The first one focuses on molecular solids as temporary adhesives, and I'll give you a glimpse into that research area towards the end of my talk today. But by far the most central thrust for us is the development of materials for electroanalytical applications, and that'll be the majority of what I'll talk about today. But some of those materials that we develop, we also apply for energy and environmental applications, mostly through work with collaborators in battery-type devices, proton conduction, so we kind of span beyond sensors as well. Of course, this is my view of what my group does. I think my students' view is a little bit different, maybe more like a continuous saga with a sequel and a prequel and no end in sight. Anyway, one of the major thrusts for us is the innovation in materials chemistry aimed at chemical detection in the age of information. So we all, at this point, probably carry portable electronic devices in our pockets. And what we want to do in my group is to merge the power of that portable electronic platform with chemical detection to enable better healthcare, better personal protective equipment, and other applications that could be connected to merging chemical sensing with a really portable detection platform based on the smartphone. And for that, we need materials that can actually integrate into that kind of low power requirement. And also devices that are really miniaturizable and can basically integrate into that platform. And there's been quite a bit of development of miniaturized sensing devices, starting with physical sensors. This is just one example from John Rogers' group of an electronic tattoo that integrates temperature sensors into it, strain gauges, and other physical detection capabilities like heart rate. But going beyond that, there are also some nice chemical sensor technologies that are now emerging in a wearable format, like a smart wristband watch type device capable of using sweat, and in that sweat detecting analytes like glucose, lactate, and ions like potassium, sodium. And you can integrate physical sensors into that, like temperature detection as well. And here's another example from Joe Wang's group at UC San Diego. Basically eyeglasses that collect sweat from the nose area, and with that are capable of detecting potassium ions and then also lactate. What is common to these specific sensor technologies and other sensor technologies in the portable format that do currently exist is the reliance on carbon-based materials that are then post-synthetically functionalized with either ionophores to enable detection of ions, so supramolecular receptors, or enzymes to enable detection of things like glucose and lactate. And while that strategy does work, it has some limitations. First of all, you're creating heterogeneous interfaces that are limited in stability, prone to delamination. But also, what you might notice is that many of these existing sensor technologies detect the same sorts of things for which we have good supramolecular approaches, like ions, glucose, lactate. And if you want to go beyond that, you need new materials. And so that's where we come in. So where might we want to go beyond that? So my group is specifically very interested in a class of 3 gases, carbon monoxide, nitric oxide, and hydrogen sulfide, that are toxic by inhalation at part per million exposure limits, but are also critical to life and modulate a number of important physiological processes, ranging from blood pressure regulation to immune response to possibly also learning and memory. But exactly what they do in the body is not very well understood. And some challenges associated with that understanding are twofold. One is that their concentrations in the living systems are pretty broad, ranging from nanomolar to millimolar concentrations in the bloodstream, for example. But 2 is that their half-lives in vivo are also extremely short, ranging from seconds to minutes. So what we need are sensors that respond very quickly, but also give us a broad dynamic range that can work across these concentration ranges. So the way we look at our technology development is in 2 ways. We want to develop materials and understand material analyte interactions for these gases with a long-term goal of these materials being biologically or biomedically relevant, detecting these gas transmitters either in exhaled air or within the bloodstream or other body fluids. And that could make an impact in understanding and treatment of some of the diseases that are associated with the misregulation of these gases in biological systems. But also, because these gases are toxic by inhalation, the technology that we're developing could serve the basis for environmental monitoring, personal protective equipment development, so it could be a multifaceted type of approach. So what I'll talk about today is mostly detection of these gases in the gas phase with relevance to personal protective equipment, and environmental monitoring. But keep in mind that we have a long-term goal in mind, and that's the direction that we're still headed in. And what we're doing right now is basically building the fundamental understanding of how these materials work and what their interactions with these gases are like. So the materials that we focus on are metal organic frameworks. We see these materials as being bio-inspired. We don't try to mimic biology, but biology provides inspiration, like in proteins that can detect and differentiate these small reactive gases, such as guanylate cyclase. So within the proteins, there are well-defined molecular recognition subunits that can bind the gas, and then that binding interaction is transduced biologically with protein change in shape. And that provides signal transduction and then regulates a number of physiological processes. In our materials approach, we want to have the analyte trigger a sensor response that is basically triggered by the interaction of the analyte with the surface of the material. And we want that sensor response to be electronically transducible, again, with the goal of coupling it to information technology and smartphone-based detection down the road. So we can produce that sensor response through a change in conductivity, work function, dielectric constant, but one of the easiest ways to do that in an electronic device is a change in resistance. And that can then have applications down the road in healthcare, industrial safety, environmental stewardship. So I want to give you just some of the reasons from the perspective of electroanalysis why the particular framework materials that we've selected for our work are beneficial in this context. So we work with conductive metal organic frameworks, and they're conductive because we want that electronic transduction mechanism. And you can kind of view them as synthetic graphene analogs. It's a two-dimensional d-pi conjugated material that in a way is graphene-like and can be exfoliated into thin sheets, but has metals embedded within the basal plane of the material that can give us ability to bind gases and then transduce that change electronically. So one of the reasons that we think these materials are particularly well suited for these electroanalytical applications is because of their chemically precise extended structure. So unlike most synthetically modified carbon-based materials, this material is accessible as a crystalline structure through bottom-up self-assembly. Its conductivity is very useful for electronic transduction and actuation of chemical information, which is beneficial in this context. And additionally, we have embedded porosity within this rigid structure, which gives us high surface area for interacting with the molecules that we're trying to detect, and high volumetric capacity for capture as well. And then finally, we have a modular structure in metal and the ligand, and that gives us reconfigurable control over the properties and the surface chemistry of the material. So taken together, we think these are really promising materials for electroanalytical applications that give us very precise control over surface chemistry. So these MOFs are extremely diverse, and I will talk about mainly two examples of triphenylene-based MOFs originating from the triphenylene ligand, interconnected with divalent metal ions, and also based on the metallophthalocyanine. So once these MOFs are synthesized, we can place them into a variety of electronic devices like amperemetric detection, voltammetry, and potentiometry. So today, I will mainly focus on amperemetric detection and chemoresistive approach, where we're basically using the device based on the metal organic framework as a variable resistor that will change its resistance in the presence of a chemical. But keep in mind that that is not the only way to read out electronic signal from these materials. We also have demonstrated the ability to use them as working electrodes in voltammetric detection of neurochemicals and as ion-to-electron transducers in potentiometry. So it's a really multifaceted materials platform. The nice thing about these materials is that they're really easy to make. So starting with hexahydroxytriphenylene, which is commercially available, although we do make it in my group, to control the purity and the quality of the ligand. And then reacting that ligand in water under air with a metal acetate salt with just a little bit of heat, you can get very nice nanowires of these materials that basically precipitate from solution. They're conductive and porous and can be exfoliated into thin sheets and visualized in their hexagonal porosity using transmission electron microscopy. We have graduate students, high school students, undergrads making these materials. The synthesis is relatively straightforward for this particular class of MOFs. And they are very stable. We are making them under air and in water, so they're stable to those conditions and provide us with a very robust platform with which to work with. So we have a variety of ways of integrating these materials into devices. But the way we started in my group, and this was when I was an assistant professor at Dartmouth, I just started, my lab wasn't ready, and we just wanted to hit the ground running right away without much infrastructure in place, is we basically decided to draw the electrodes on a shrinkable polymer film. So we're just drilling with number 2 pencil. These are conductive carbon-based electrodes. The shrinkable polymer film is a pre-stretched polystyrene. They're marketed as Shrinky Dink toys. I don't know if anyone has played with them, basically for kids. What you can do is heat it up, and then the features get miniaturized. So there's lateral shrinking. It has to go somewhere. So it increases in thickness, but that's fine. And so that gives us nicely miniaturized electrodes that are made of carbon with size features that we wouldn't be able to draw by hand. So sub-millimeter scale electrodes. And that provides kind of a miniaturized device architecture, minimizes the amount of the material that we have to use, and that interdigitation makes a better contact to the material than just a gap electrode. So what we then do is dip this electrode array into the solution phase precursors for the formation of the metal organic framework, and just let the MOF grow directly into the device and deposit itself and connect to the electrodes. From that, we obtain ohmic contacts, so good contacts, electrical contacts between the electrodes and the MOF, and we can begin to do device testing. So some characterization, these are our electrodes. As the MOF grows into the device, we see the characteristic features of the metals that are coming in from the metal organic framework formation. These are the films of the metal organic frameworks on the device, and then this is the nanowire morphology. So the devices that we're testing are basically arrays of randomly oriented nanowires of the MOFs, and that's important to keep in mind. We're not yet working with monolayers, we're not working with epitaxially oriented crystals, so the response is going to be coming from this kind of bulk system. And it's likely going to be the junctions between the crystallites and the surfaces of these nanowires that are going to dominate what we see in chemical sensing. So for a chemiresistor, basically we expose it to a chemical, and if this is a functional material, we expect the resistance of that device to change in the presence of different chemical environment. So this is just basically a variable resistor. The raw data looks something like this. It's a current versus time plot. As the analyte is dosed, you see a change in current. As the analyte is basically blown off with a nitrogen stream, you see some recovery. So with the data that I'm going to show, of course, the magnitude of response is going to matter. We quantify that. But keep an eye also on the reversibility, because something that's fully reversible is indicative of fully reversible chemical interactions. Something that's partially reversible, like the data shown here, has something related to chemistry that is not fully reversible. And then there are completely dosimetric devices also that we see, which is also related to the irreversibility of the chemical nature of the interaction. So we take this data, put it through a normalization procedure. This is basically negative inversed conductance that we're looking at. It's proportional to resistance. So when you see this vertical axis with these conductance values, just think of it as change in resistance. And normalization allows us to compare multiple devices together in a very straightforward way. So let's take a look at some data. Here we're exposing these shrinkable polymer films with MOFs on them to 3 different analytes: ammonia, nitric oxide, hydrogen sulfide. We have 2 MOFs, copper, hexahydroxytriphenylene and nickel hexahydroxytriphenylene. So same ligand, different metal. And we see some features of the data. So there's a lot going on here. So I just want to draw your attention to three main features here. One is that we have a concentration-dependent response. And there's a linear range in that concentration-dependent response that allows us to determine limits of detection, which turn out to be in low part per million values. Two is that we see some selectivity in response. So depending on the nature of the metal, we see a different response. For example, when looking at ammonia, the nickel-based system does not produce any significant change in resistance. The copper-based system does, and it's a reversible response. Two is that we have a different directionality of the response. So if you look at oxidizing gases like nitric oxide, you can see the resistance goes down, so the system becomes more conductive. Whereas for hydrogen sulfide and ammonia, the resistance goes up. So that is a typical behavior of a p-type semiconductor. So when exposed to an oxidizing gas, it becomes more conductive, the resistance goes down. When exposed to a reducing gas like H2S, the resistance goes up. So that tells us something about the transport through these materials, through the gas exposure. A little bit indirectly, but still informative. And then there's a different magnitude of response for different materials, and that's also valuable. So we can take that data and put it through a principal component analysis. This is basically like a machine learning technique that allows us to take the data and show that we can differentiate these gases from each other and also from water vapor. That potentially bodes well for selective detection down the road using arrays of frameworks that basically work together. So we're interested not in just applied nature of these devices, but in the actual chemical nature of the interactions that are happening between the materials and the analytes. So for that, we perform spectroscopic investigation to probe the material-analyte interactions. Like I said, because we're in the nanowire morphology, likely we're going to be dominated by the edge sites on these nanowires in terms of how the sensing response emerges, but we can also keep in mind what might be happening on the basal plane. So for these triphenylene-based materials, we envision some really simplistic interactions with ammonia, Lewis acid interactions of the metal with the ligand, or Bronsted acid interactions if we have aqua-capped metal sites, and then we can have hydrogen bonding between ammonia and those waters on the surface. So performing diffuse reflectance infrared spectroscopy tells us that for these triphenylene, hexahydroxytriphenylene-based materials, there's actually both Bronsted acid and Lewis acid sites that are present. But what is important is the distinction between what happens with the copper-based system and the nickel-based system. So with the copper-based system, which starts out as a mixed valency type material, there's some copper 1 and copper 2, the population of the copper species shifts towards copper 2 upon exposure to ammonia. We rationalize that as perhaps a metal to ligand charge transfer. But for the nickel system, we don't see any significant changes in oxidation states. And we probe that by electron paramagnetic resonance, but we also have XPS data, so X-ray photoelectron spectroscopy data, to back that up as well. So taken together, this begins to paint a picture that in the case of copper, when ammonia binds to the surface, there's a change in the electronic characteristics of the material that are transduced and change the transport flow of charge through that material, and that results in the chemoresistive response. But for the nickel-based system, there is no significant perturbation to the electronic properties of the material, despite potential binding to the surface, and that gives no response. So what's important is not just binding to the surface, but some kind of electronic transduction of that binding event for us to be able to read that signal out electronically. Okay, with nitric oxide, what we believe is happening using the combination of the same techniques is that we're actually oxidizing nitric oxide to nitrite and nitrate species, but there's also some binding of NO to the metal centers. The crystallinity of the framework is preserved despite exposure to high concentrations, even 10,000 ppm nitric oxide. And then with hydrogen sulfide, using the same techniques again, infrared spectroscopy, XPS, what we believe is happening is that there's formation of sulfur 0 species on the surface of the MOF, but there's also copper sulfide formation, and the crystallinity of the MOF does begin to break down when we expose it to high concentrations of H2S, like 10,000 ppm. When we're looking at just 80 ppm, it's not a significant change in crystallinity, and we don't see formation of copper sulfide type species. So our device integration strategies are not limited to these shrinkable polymer films. There are other ways to put MOFs into devices. But what we have prioritized in my group is really combination of the templated synthesis of the MOF into the device. So we want the MOF to make itself and then put itself into the device. So kind of like a Lego material assembling itself and building itself into position. So to do that, we can perform the synthesis of the framework in the presence of a textile swatch. And what we observe is formation of electronic textiles that are conductive, where we get conformal coating of the textile fibers, this is cellulose in this case for cotton, by metal organic framework crystallites. And it's about 8% of MOF by weight in this textile composite. It's a mechanically stable device. We can bend it, we can flatten it out, twist it, and what we see is actually really good stability of the resistance to these mechanical perturbations, which is good because we want to be able to make chemical sensors and not mechanical sensors. And we rationalize this by the fact that we're well above the percolation threshold of charge through this material. So when we're bending it, the crystallites are not separating that far apart to influence the conductivity of the overall system. So we can place this textile into a custom-made enclosure and then expose it to some of these same gases that we were talking about. In this case, we're taking two framework materials, both with the nickel metal, but different ligands. Hexaaminotriphenylene connected with the nitrogens here as the heteroatomic crosslinker, same triphenylene building block for the organic portion, and then hexahydroxytriphenylene in red. So a couple of things to point out about this data. We have dosimetric response for these materials towards NO and H2S, consistent with that same chemistry that we talked about that is irreversible. And we have a P-type semiconductor response of the material in red, where resistance decreases in response to nitric oxide and increases in response to H2S, but that's different for the material in blue. So with the nitrogen crosslinks, what we see is more of a mixed type or an N-type semiconductor where the directionality of response towards NO is in the opposite direction for the oxygen analog. And that's helpful because we can take this array with a different response and again use principal component analysis to show that we can not just detect, but also differentiate these gases from each other. What's really cool about the system is that when we humidify the gas stream, the sensing performance is retained and essentially indistinguishable from the dry nitrogen state, which potentially bodes well for applications down the road. But perhaps what is most remarkable about these systems is because of the irreversible dosimetric response and the chemistry that's happening on the surface, we believe that we're not just sensing these gases, but have the ability to filter them as well and to use this porous MOF textile composite as a filter. So at that point, we were not collaborating with Professor Ibarra, so we had to kind of make a device that showed some ability of the MOF to retain the gas. So we do that by placing two devices in series. So we put two devices into this custom-made enclosure. We flow the gas not over the surface, but through the devices. And then we see what happens to each of the sensors as we do that. So what happens is that the response of the second sensor is attenuated by the presence of the first. So the first sensor begins responding right away. That's the solid line in all the sensing traces. And then the second sensor has a delayed onset of response, the dotted lines, and we believe that that mismatch is due to the filtration capability of the material. So we have a variety of methods for textile integration in my group, and I just want to highlight this one particular example that was serendipitously discovered by one of my students, the first PhD student from my group, Michael Coe. And this particular method basically takes copper, solid metal, 0, and converts it to the metal organic framework in the presence of water and oxygen at room temperature. So this is a super mild transformation. Doesn't really get milder than that. And the source of the metal is coming from the pre-deposited copper on cotton that can be deposited by thermal evaporation, but there could be other ways to put down metal on the textile. So what this particular technique gives us is really remarkable orientation of the crystals on the surface of the textile, and also excellent adhesion to the surface that we believe is promoted by this pre-templated copper metal that we pre-deposit on the surface. This technique is amenable to patterning, so if we pre-pattern the metal, we can convert that pattern to the metal organic framework under those conditions. And the pattern fidelity is retained really well on sub-millimeter scale. So here I have a short video where my student describes this technology. So take a look, hopefully this works. And you also get a little bit of a bird's eye view of Dartmouth campus.
Hi, I'm Aileen Eagleton, and I'm a graduate student in the Mirica group. As part of a team, I developed a robust method to form a conductive metal organic framework on a textile substrate. In this process, I deposit copper on fabric through thermal evaporation. I restructure the metal into a metal organic framework by placing the copper textile in solution with organic linker. This method combines the synthesis of framework material and the fabrication of an electronic textile. This process of installing conductive material at the fiber level could become a platform technology for producing scalable, multifunctional electronic textiles.
Right now the campus looks a little bit different because we have snow, but it also really nice like that. Okay, so this particular system is capable of very robust performance. So not only is it capable of sensing, but we can retain that sensing response even when we put our MOF textile composites through a variety of physical and chemical tests. So like abrasion, ironing, washing with detergent, peroxide, and bleach. And that can withstand even multiple cycles. Does really well at detergent washing. Peroxide at 30% and bleach begin to basically degrade the MOF after multiple cycles, and so the metal begins to leach out, and that's the diminishment in performance. But we're still sensing, so it's not too bad. So kind of to summarize all of that, what we talked about so far are metal organic framework-based materials and their integration into devices through self-assembly, and why we have been able to achieve part per million detection of analytes of interest like these gasotransmitters. If we sort of step back and think about, is this good enough for biological applications that we envisioned at the outset? Probably not. We need to be more in the part per billion sensing regime. But it certainly is good enough for applications in personal protective equipment, sensing with relevance to that, hopefully filtration and detoxification of these gases as well. And we think this could have potential impact in healthcare, protection, and there's some potential for global scalability because everyone wears textiles, so they're really ubiquitous, and maybe one day you'll see MOFs and textiles that you can buy. But as we push forward towards more biomedically relevant detection, what we decided to do is take a step back and rethink the materials design. and add an additional receptor to the system based on this metallothiocyanine system. So we've done quite well so far using these metal bis-dioxylene linkages to achieve part per million detection. But what we reasoned is by integrating a metallothiocyane receptor into the MOF, we would be able to maintain ppm sensitivity with this node, and then have another receptor that could maybe bring us into part per billion sensitivity with the metallothiocyane building block. There's good precedent for gas detection using thiocyanines, but with molecular solids of these entities, there's a requirement for high driving voltages, so that wouldn't be compatible with the kind of low power devices that we're seeking to develop. So we embarked on the synthesis of this bimetallic metallothiocyane-based MOF, and with the leadership of a fantastic postdoc in my group who's now in an independent position in China at USTC, we're able to synthesize crystalline materials using metal acetate reacting with the octahydroxythiocyane using copper and nickel-based nodes. So these exhibit chunk-like morphology, but can be exfoliated into thin sheets where their square porosity can be visualized again in transmission electron microscopy, and they have moderate conductivity. So these are semiconductors with conductivities in the range of 10 to the minus 2 to 10 to the minus 4 Siemens per centimeter. So let's take a look at some sensing responses. For H2S, we do a lot better. So we get to part per billion sensitivity as we do with NO. So this really did help. And we attribute this improvement in performance to the chemical composition of the material. But to really understand if that's the case, we're doing more ongoing studies on structure property relationships to understand how different building blocks contribute to the sensing response. So there's a variety of these bimetallic MOFs that we're currently synthesizing, studying their material analyte interactions using spectroscopy. But what we also decided to do is to use a perturbational approach and change this linker from the metal to an organic portion. So instead of a metal organic framework, have a covalent organic framework that is linked with these really robust pyrazine linkages. And it's a conjugated, pi conjugated material that we thought, based on the design criteria put in place of a flat pi conjugated system, would be a conductive covalent organic framework. Now, conductive MOFs are tough. Conductive COFs are even tougher. So this took some time to put together. But again, with the leadership of Zhang Meng, we're able to get to the molecular precursors of these systems, these octa-aminothiocyanines. And the bottleneck here is really on the synthesis of the ligand. Once we have the ligand, we can perform the condensation reaction with pyrene tetraone and basically have the covalent organic framework that is relatively crystalline and porous. Now, we named this after a COF. We named this after DC 8, Dartmouth College 8, because this was the first covalent organic framework of its kind. And DC stands for Dartmouth College 8, for the lucky number 8 of the octa-amino functionality that gave us trouble in terms of getting to the material in the first place. But as I kind of went around and talked to people about this, someone pointed out there's a retired plane called DC-8 that now serves as an airborne science laboratory for NASA. So now my goal is to have our frameworks fly one day as sensors monitoring air quality on this DC-8 plane. Okay, so this framework has a nanowire-like morphology that we can visualize. Again, TM tells us something about the porosity of the material, but perhaps what's most remarkable about this covalent organic framework compared to the metal organic frameworks that I talked about so far is the exceptional thermal and chemical stability. So we can heat this material up to 500 degrees Celsius and it maintains its weight in thermal gravimetric analysis. We can expose it to concentrated acid and concentrated base, and it maintains its crystallinity. So it's pretty robust, and we attribute that to these robust covalent pyrazine linkages for this covalent organic framework. So in terms of sensing response compared to what we did with MOS, we take a hit in terms of sensitivity towards H2S. So now we're in like hundreds of ppb limit of detection. But actually for nitric oxide, the sensitivity is maintained. And the change in resistance is very significant. So we're looking at thousands of percent change, which gives us a really nice signal to noise ratio to work with. So what have we learned from these structure property relationships? Well, for the detection of H2S, the copper-based nodes definitely help. We get much better sensitivity with the MOF that contains copper. But for nitric oxide, actually, the covalent organic framework does quite well. And that may be attributed to the phthalocyanine moiety, but also to the organic portions of the framework that could get oxidized in the presence of NO. Ta-da! So let's sort of reflect back on what we talked about so far. So we have a MOF analog and a COF analog, and taken together, they can give us some understanding of the structure property relationships of these materials. And even though I talked about just one device architecture, there are many other possible applications for these materials. So we've demonstrated the ability to detect small reactive gases. I didn't talk about detection of carbon monoxide, but we can do that as well. We have high modularity in terms of molecular design for sensitivity, and the way we're approaching selectivity is through arrays. So making arrays of cross-reactive materials that together can serve as an electronic nose that can basically do pattern recognition, just like the human nose can. So some of the advantages of these systems over other methods of detecting gases is that these offer truly low power consumption that could be from millivolts up to a volt. So it could be operated by a portable battery very easily. We have room temperature operation, which is unlike metal oxide semiconductors that need high temperatures for their operation and so consume a lot of power. And although these seem like designer materials, we only actually are using micrograms of material per device. So for the actual sensing, we don't need that much. And designer materials could be okay in that realm of applications. We have good performance in the presence of humidity, but of course, we need to really validate it in the presence of mixtures and more complicated systems of gases. So with that, I'd like to conclude. If you're interested in some of the work that we're doing, I can refer you to some of the papers that we have. How am I doing on time? Do I have time? How much time?
Yeah, you have like 15 minutes.
Okay. So yeah. So since there's time, what I want to do is kind of switch gears to a different part of my group and tell you a little bit about these sublimable adhesives that we've been developing that we think could make an impact in microelectronics. So the development in microelectronics has followed the pace with Moore's law. This is Gordon Moore, who was a chemist, and his personal wealth exceeds that of Dartmouth's endowment. So if you're thinking about, whether a chemistry PhD is worth it, I definitely think he's a great example showing us that it is. But he, back in the 1960s, proposed this idea that was later named after him of basically pushing the pace of electronic device development that would double approximately every 2 years. And the devices have kept pace with that to some extent in terms of packing more transistors into square surface area on a chip of a semiconductor, but also in solid state, memory development, and other features of electronic devices. But while Moore's law has worked quite well, to some point we've basically reached a limit in 2 dimensions in terms of packing and cramming more and more features into the 2-dimensional space. So perhaps we should start thinking about making circuits like we make skyscrapers with functional interconnects, not just in 2D, but in 3D, in a layered fashion. And that is basically what the microelectronics industry has done with the solid state memory development. So many of you have some kind of solid state memory stick or something like that. And that hasn't really changed in its form factor for a couple of decades at this point. But there's more and more memory that is getting crammed into it. And the way that that's done is basically through stacking more and more layers and making interconnects in 3D between those layers, and basically making these 3D integrated circuits. This is all done on silicon, so the key feature of progress in that area relies on using a silicon wafer and making it as thin as possible so that you could cram more and more circuit components into 3D. And the way that that works is through grinding and polishing. So basically silicon wafers are taken and ground and polished to get them as thin as possible, and then stacked on top of each other after patterning. And the key part of that process of the grinding and polishing of silicon wafer actually depends on adhesives that are used. And when tape-based adhesives are used and you have a very thin layer of silicon, what happens when you try to delaminate it is that there's a very poor device yield due to breakage. And if you use liquid-based delamination for a thin material, there are surface tension effects, and that also tends to break down. So the industry is basically stuck at about a 50 micron thickness and has a challenging time going beyond that. So this project emerged through a collaboration at MIT where I was sort of brought in as a chemist to consult for it, but has since then kind of flourished into a portion of my own research program as we kind of got going in this area. So what we wanted to do is to eliminate the tape from the processing of semiconductor wafers. And the way that we reasoned that we might be able to do that is to have sublimable adhesives. So we could melt bond the silicon wafer to a carrier substrate that was porous, and then process and take it through these grinding, polishing, and other functionalization steps. And once that process was complete, release the wafer from the carrier by sublimation. So that would be a very gentle process without the need to use a mechanical force or without the need to use any solvents. And we decided to start with polycyclic aromatic hydrocarbons for that, just to demonstrate the principle, because they are known to be meltable and sublimable, and their physical properties are very well defined, and there's a range of functional groups that we could rely to achieve adhesion to the surface. So we tested a range of polycyclic aromatics in their adhesive strength to glass. This is glass, but this is relevant to silicon because ultimately silicon has silicon dioxide layer on top, and this is kind of a prototype system in a very straightforward way. So what we found actually is that polycyclic aromatics were actually quite good at holding glass surfaces together. This is double-sided tape, so Scotch tape, so naphthalene and hydroxylated versions of naphthalene are basically as good as double-sided Scotch tape, which is comparable to the strength of adhesion that we want in the system. So the way that this system promotes adhesion is through preferential orientation. So we can characterize our adhesive films. They're in the micrometer thickness range using light microscopy, polarized light microscopy, and also characterize the fracture of adhesion for different materials. So this is naphthalene. It undergoes adhesive fracture, so it fractures from the surface, delamination of the polycyclic aromatic from the surface. For the dihydroxy naphthalene, actually we get cohesive fracture, so it rips through the material. So the material itself has limited mechanical strength, but its adhesion to the surface is actually quite good, promoted likely by hydrogen bonding interactions of the hydroxyl groups to the silicon dioxide. So we looked more into this by powder X-ray crystallography, basically looking at preferential orientation, and we're able to make some conclusions that the crystals are oriented with respect to the glass substrate, and that adhesion is promoted for the hydroxylated systems by likely hydrogen bonding interactions. This works not just on glass, but actually on silicon wafers. So we can take a real wafer, we can adhere it to a porous carrier, take it through processing steps of grinding, polishing, and dicing, and then achieve delamination, it holds up. This is not limited to polycyclic aromatic hydrocarbons. Actually, a variety of sublimable solids can also promote these adhesive interactions. And this is just some examples of some of the molecules that we've tested. And what we found in this particular study is that camphor, a terpene, naturally occurring molecule, is really good at holding surfaces together, basically comparing in its strength to basically like super glue. So just to give you kind of a qualitative feel for how strong that is, this is like a 2 by 2 centimeter glass slide area that's bonded by camphor, melt bonded, holding up a 50-pound dumbbell. And it can be very easily debonded by sublimation. So let's see if this video plays. So if we put it in a sublimer apparatus and then put it under vacuum, we can promote sublimation, and once some critical amount of the material has evaporated, you can see it basically falls off against gravity. So my students took matters into their own hands and suspended themselves on metal coupons bonded with camphor. This was done while I was out of town, maybe for the best. So it's pretty strong, kind of remarkably strong. And the strength of adhesion is again promoted by preferential orientation of the camphor crystal to the surface, hydrogen bonding interactions, but also a really interesting supramolecular structure of the camphor itself that has a helical twist, and those helices are aligned to oppose mechanical fracture when we bond these surfaces through melt bonding. So yeah, it's just a visualization of camphor oriented on the surface of glass. All right, so with that, I'd like to conclude. We think these molecular solids, these temporary adhesives, could have a variety of potential applications in terms of adhesion science. It gives us conformal contact of surfaces through melt bonding, gives us a range of adhesion forces to work with, and we have controlled release based on sublimation. We think some of the supramolecular principles of adhesion and mechanical properties of crystals could be applicable to other areas like organic electronics, pharmaceutical tabletability, and safety of energetic compounds, along some other possible applications as well. Okay, so I'd like to conclude and thank my group. They're a fantastic group of people to work with, and I'm really grateful for their willingness to go into uncharted territories with me. I want to thank the sources of funding that have supported our work over the years, and thank you for your attention. I'll be happy to answer any questions.
All right, thank you so much. Shall we start with questions? Students, anybody?
Shall I have one?
Yes, I need. Go for it.
You spoke of MOBs, and I think you changed the metal on the MOBs to see what was the effect of that in the conductivity or the sensing of the molecules that you had. Did you change, or did you try to change the linker or modify it with electro withdrawing groups, or maybe donor groups in the linker, maybe to make it better?
Okay, so the question is, did we change the linker to somehow improve?
To put functional groups.
We have not done that yet, other than like using, hexahydroxytriphenyline versus hexaaminotriphenyline. So a little bit on the way that the cross-linking is done. We have done some studies, I didn't show that here, looking at the difference between phthalocyanine and naphthalocyanine, so extending the pi backbone of the ligand to make the pore larger, but also change the electronics of the system. What we found there is that it didn't have a huge effect, or it didn't make the system better. I think it has the opportunity to do that, and perhaps could be well done computationally to give us guidance of the kind of properties that we might expect and whether the system is worth pursuing. I think it should definitely work in some contexts, for sure.
All right, anybody else? Juan.
Thank you for the nice presentation. I have like maybe a silly question, but like in the first part of the presentation, like this mob like have a local metal size, right? Like the copper. I don't know if you use the mob like the active example or when they are like with water. Is like a difference in the response when you exposed to the gas.
Yeah, so the question is like, is the way that the device is prepared or the way that the MOF is activated going to influence the response? Probably yes. So one thing I want to say is that for many of these MOFs, these conductive MOFs, the single crystal structure resolution is not available. So we're kind of inferring a lot of things from PXRD, some simulations that others have done. But for the systems that do have some crystal structures, so like for the nickel and cobalt triphenylene, hexahydroxy triphenylene based system, they're aqua capped. So there's definitely water ligands there. For the copper system, it's believed to be an open metal site. But when we grow it from water, and we don't activate these devices at very high temperatures or just let them air dry, there's likely water on the surface, water in the pores, that is likely going to influence what is happening. So that's an important thing to pay attention to, and we're starting to do that now more systematically. So as long as the devices are prepared in a consistent way, we get consistent responses, but one has to be careful about those preparation conditions and mindful of what might be happening on the surface. Yeah.
Okay, anybody else? Pablo?
Yes, thank you, Doctor. This incredible talk. Really nice work with what you're doing with all these materials. But I have a kind of silly question too, maybe. You said you were using 2D MOFs to make sheets, and you were talking also about making a stack. But why not 3D MOFs?
3D MOFs would be the way to go. If we could have conductive 3D MOFs that gave us the opportunity to take advantage of the supramolecular chemistry, within the pore, and also the sterics, coupled to the electronic transduction, that would be great. The challenge with conductive 3D MOFs is that there aren't that many options, and they're not that conductive. So to drive camera-resistive devices with 3D MOFs would be a challenge. You'd need like really high powered, 10 volts or more, working with really moderate conductivities of like 10 to the minus 7 to 10 to the minus 9 Siemens per centimeter. So there's that challenge. But as more 3D MOFs emerge that are conductive, I think that would be definitely a great approach.
Okay. Jorge.
Yes, well, before the question, thank you so much for this talk. It was very nice. Thank you. And I would like to know, you have presented application related with the electronic devices. What do you see in the future for the MOFs for other applications? Not electronic device, because you are developing that. Because there are a lot of people working around MOFs. What do you see for application, technological application?
So let me maybe clarify that by asking, do you mean MOFs in general or conductive MOFs?
Conductive MOF.
Okay, because I'm obviously biased in a certain way. I think for conductive MOFs, the applications that are most suitable for this system would be those that combine the conductivity of the MOF with something else, like electrocatalysis, for example. And we have done some of that with like CO2 reduction, using them as electrodes in batteries. I think there are many opportunities. There are some applications that are being developed for spintronic devices. It's still in the realm of coupling that electronic conductivity with something else. But I think that's where conductive MOFs are really unique, is when you capitalize on the electronic conductivity. Because if you don't need that, you have a lot more MOFs to choose from, and those could have broader, far-reaching applications.
Okay, thank you.
Valeria.
Thank you for your very good presentation. I would like to say that I love your Dartmouth textile, and I want to ask you that how compare your materials with the conventional materials, conductive materials?
In what way? Like compared in what way? Conductivity.
Conductivity.
Certainly, conventional conductive materials can be more conductive than what we have. So just to put that in perspective, metals, of course, are going to be more conductive than any semiconductor that we're going to deal with. But compared to like some of the semiconductive materials, like let's say carbon nanotubes, these definitely lag behind in conductivity. So they're moderately conductive, but that I think has its place. But it depends what applications you want. Like in the chemiresistive device, that's fine. As an electrode by itself, in a liquid phase electrochemical system, these semiconductors by themselves have a hard time being a standalone electrode. There's just too much resistance.
Just I cannot go without asking this. How did you get the structure of the DC-8? Did you get the powder or did you
It's
get
a
crystals?
powder. No,
Okay.
I wish we got crystal. No, it's a powder.
Okay.
And that took a while.
Yeah. Okay.
Yeah.
Imagine.
Yes.
Thank you very much for the night talk. I enjoyed a lot. I have a question. You said at the beginning of the talk that you can detect many toxic gases. You talk about only three gases. What happening about carbon dioxide, for example, or sulfur dioxide? It is possible to detect with this kind of materials?
It should be possible. SO2 we're doing now. So we're moving in that direction. Carbon dioxide, there's a demonstration from Mirica's group that also can be possible.
Or maybe you need to do a design of the other type of materials to detect or to pick up the carbon dioxide, or maybe, I don't know.
Yeah, I mean, there's two issues, right? So first you have to bind it, then you have to transduce that interaction. Of course, it's much easier with things that are strongly reducing or strongly oxidizing, and that is part of the reason why we went for the low-hanging fruit in that realm. The things you're mentioning are harder. And so that's where molecular design can definitely make a difference, and thinking strategically about interactions, but also electronic perturbations to the material will be key for that.
Anybody else? So I'll have the honor to ask the last question. Taking the advantage of things that we already know and something that you already published, I'm thinking about textiles for catalysis. Because, for example, taking the example where you know the H2S is converted into copper sulfide, right?
Yeah.
So I was thinking, now you have very elegantly demonstrated that by a low loading of the mouth on the textile can do detection. But now that we know that it converts and very nicely and very easily, room temperature, atmospheric pressure, just a little flow of it. Would it be crazy to think about membranes with a little bit more of the material on the textile in order to do the catalytic conversion in situ?
I think that's totally doable. I don't know who wants that
Well, I was thinking about catalytic converter like in cars.
in cars.
Right?
Yeah. Could be. Yeah, I think that could be doable. With like an appropriate membrane, without any added power, you have the chemistry built into the system to basically do that conversion. So
on top of detection, you're doing catalytic conversion.
yes.
Beautiful. Beautiful. All right, guys, so thank you so much. Can you just join me in a round of applause for Katherine? Thank you so much.